Welcome, everyone. Thank you so much for having me. And a huge hello to all you future materials scientists out there. Think of today's explainer kind of like a special guest lecture. We're going to be exploring the rapidly expanding, frankly mind blowing frontier of AI and machine learning in our field. AI is literally transforming how we explore complex phase spaces. But to truly harness it, well, we need to understand exactly what it is doing and, maybe more importantly, what it isn't doing. Okay, let's dive into this, because this quote by Nobel laureate Melvin Calvin pretty much perfectly captures our core challenge today. As scientists, we are incredibly good at finding solutions to problems we already know exist, right? But the true promise of AI is its potential to help us grapple with the vastness of the unknown unknown. It's that massive difference between just finding a slightly better version of what we already expect versus discovering something entirely unprecedented. So, here is our syllabus for today's lecture. 1. Welcome to AI Materials Science. 2. The Deep Learning Framework. 3. Breaking the Banana Curve. 4. Navigating the Kessel Run. 5. The Search for Unknowium. And finally, 6. Keeping Humans in the Loop. Let's get right into it. Welcome to AI Materials Science. To really demystify our subject here, it is so incredibly easy to look at AI as this magic black box, right? You throw in some numbers and boom, out pops a miracle material. But fundamentally, AI is just a highly efficient computational tool for processing structured labeled data. Think of it through a really simple analogy. You've probably all seen AI image generators. They work by looking at millions of pixels and gradually extracting these higher-level abstract features until they recognize, say, the shape of an eye. Well, deep learning in material science works the exact same way, just with different data. Instead of pixels, the model processes atomistic coordinates and element types to recognize the features of, for example, an FCC crystal. It's extracting abstract composite representations, entirely unleashed from those underlying numerical values. Section 2. The Deep Learning Framework. Let's see how this builds into the modern methodologies you'll be reading about in the literature. We frequently see AI and machine learning studies falling into a framework we can call the DEEP moniker. That stands for Discovery, Exploration, Explanation, and Prediction. Categorizing your work within this DEEP EEP framework really helps clarify both the intent and the actual output of your machine learning algorithms. Basically, are you just mapping a library of properties, or are you looking for an entirely new phenomenon? And this brilliantly illustrates exactly what we mean. It grounds those super abstract, deep concepts onto something I know for a fact you've all stared at in your core classes: Ashby plots. If we reduce a really complex, multidimensional phase space down to just two properties, we can map exactly what AI is doing. Exploration expands a known cluster of data. Explanation draws a line, extracting a brand new relationship between those points. Ultimately, the entire goal of DEEP is to identify missing materials, whether that's through discovery of some unanticipated result way outside the cluster, or prediction, making the non-existent existent in a totally new regime. Essentially, you can think of these algorithms as a kind of simulated microscopy. They map out these crazy multidimensional relationships and the blank spaces on our Ashby plots that we just simply couldn't see otherwise. Section 3, Breaking the Banana Curve. To understand why we actually need AI to map these blank spaces, we've got to pivot and look at the fundamental limitations of traditional materials design. If you recall from your mechanics classes, there are these classic trade-offs we constantly fight against. The most famous one, the strength-ductility trade-off in metals. If you engineer a metal to be stronger, you almost always make it less ductile, and vice versa. When you plot these materials, they cluster into this infamous, kind of annoying sloping banana shape. Now, the top edge of that banana curve is what we call the Pareto frontier. It represents the most efficient choices available that maximize one parameter against another. And modern AI multi-objective algorithms, they are absolutely fantastic at exploring this frontier. They can find optimal configurations that push that boundary out slightly. But here is the catch. Those are still just local incremental improvements. You are stretching the banana, sure, but you're not actually breaking out of it. Section 4, Navigating the Kessel Run. Now, what's really interesting about this slide is how it forces us to take a critical look at how we're currently applying all this massive computational power. Are we actually moving forward, or are we just spinning our wheels faster? Notice how the physics of centripetal acceleration perfectly applies to our scientific progress here. Think of a satellite in orbit. It's moving incredibly fast, experiencing constant acceleration, but it's really just circling a center of mass. Honestly, a lot of machine learning studies are doing exactly this. They're accelerating the math, efficiently screening tens of thousands of combinations, but they lack an innovative direction. They're basically just orbiting the status quo of known problems. So, I really challenge you to ask yourself, if we apply an algorithm to screen 10,000 variations of high-entropy alloys for catalysis, are we truly discovering something new? Or are we just swapping months of a postdoc's grueling manual lab exploration for a couple hours of really efficient computation? Don't get me wrong, it's a flashy technique, but it's the exact same traditional progression. True scientific progress isn't just a straight, high-speed line. Think of a lunar trajectory. You have to escape Earth's gravity, manage translunar coasts, perfectly coordinate with the orbit of the moon. It is a highly nonlinear path. It requires deliberate, extremely clever changes in direction, not just tunnel vision acceleration. Okay, if you're a Star Wars fan, think of Han Solo boasting about making the Kessel Run in less than 12 parsecs. A parsec is a unit of distance, right? Not time. The Millennium Falcon wasn't fast just because it had brute force engines. It was fast because its advanced navigational computer found clever, shorter routes through hyperspace. That is the true power of AI. We shouldn't use it just to brute force known variables. We should use it as a navicomputer to find completely new, unpredictable routes through a multi-dimensional phase space.
Section 5. The Search for Unknowium.
And that leads us to the ultimate goal of AI in materials science, finding what we didn't even know we were looking for. You've probably heard the classic engineering term unobtainium, a hypothetical material with perfect properties for a known application, like, say, a perfectly efficient solar cell. But AI's true holy grail, it isn't unobtainium, it's unknownium. Unknownium is finding a completely unknown material for a completely unimaginable technological application. True discovery awaits way out there, beyond the banana curve. Think about huge breakthroughs like metal organic frameworks, or 2D materials like graphene, or twistronics, where literally just the twist angle between atomic layers becomes a whole new property dial. Decades ago, those were completely unknown unknowns. AI can now screen thousands of seemingly unrelated parameters simultaneously to find the critical relationships that lead to the next graphene. It has the power to make the non-existent existent.
Section 6. Keeping humans in the loop.
But to actually get there, AI needs you. Human intuition is completely irreplaceable in this AI-driven era. So the crucial point is this. We've all heard the old computer science adage, garbage in, garbage out, right? But in machine learning, we face a very new danger, DICO, data in, correlation out. If you throw a massive dataset at an AI, it will inevitably find a mathematical correlation, period. But that absolutely does not mean the correlation is physically meaningful or scientifically useful. And this is exactly where you come in. We desperately need a human in the loop. Your job as future scientists isn't just to press run on a Python script. No way. Your job is to curate the training data, to apply the physical constraints that actually keep the AI grounded in reality, to interpret those weird, abstract features the deep learning model spits out, and ultimately to use your human creativity to determine which of those correlations are actual, meaningful scientific revelations. Because without human guidance, without your intuition and creativity, AI just gives us highly efficient, completely predictable optimizations. As the band Radiohead sang, it leaves us with no alarms and no surprises. And honestly, science without surprises isn't discovery. It's just bookkeeping. So I'm going to leave you with this final thought for today's lecture. We possess the most powerful navigational computer ever created for exploring the material's phase space, but it still needs a pilot. Will you be the scientist who merely uses AI as a crutch to orbit the status quo? Or will you be the one who actually guides the algorithm to achieve escape velocity and discover the next unknown unknown? The choice, and frankly the entire future of materials science, is completely up to you. Class dismissed.